quizzes, let's see. There it is. All right, so today I'll go over the quiz a little bit and try to answer any questions you have, and then we will proceed on to finish landsliding. In case I forget to tell you, remind you again, we do have a midterm on Friday. So, and as I said at the end of last time, we won't cover landsliding on the stuff that's been on the quiz so far. Okay, number one, I was just looking for the flux law, essentially some form of Q mass flux per length, mass flux per width per time equal to negative bulk density times diffusivity times dz dx, or the slope. If you I said I said to describe it, write it, if you accurately defined all the variables and wrote the equation accurately, then that is enough of a description for me. But another way to describe it is that the mass flux per unit width is proportional to the topographic slope. See, number two was to write and describe the erosion deposition equation. A lot of you gave me the last thing that I derived in class and what was derived in the book. All I really needed was the more simple form that I did first in class. And the description of that is that the erosion / deposition rate is proportional to the topographic curvature. Now, if you answered that one right, then if you answered actually both of those questions right, that this flux is proportional to the topographic slope and that the erosion / deposition rate is proportional to the curvature, then you should have had no problem with 2 and 3. Because 2 simply said, okay, here's a slope sort of looking like a retreating escarpment maybe, or a diffusing escarpment. Where do you get the maximum erosion rate? Where do you get the maximum deposition rate? Where do you get the minimum elevation change? That is, erosion deposition goes to 0. And where do you get the maximum flux rate? Where do you get the minimum flux rate? Let me draw this more accurately like it was, because this tapers off to a flat slope here and a flat slope here. That means that at both of these places, we have erosion deposition goes to 0, and the flux goes to 0. Both of those places. Do the middle of the slope next. The middle of the slope here, that's where the slope is steepest, so that's where the flux is the greatest. But since it's straight, it's a straight slope there, so the curvature is 0. So therefore, the erosion / deposition goes to 0 as well. And then we look here and say, okay, that point has the maximum convexity, or the most negative curvature. something like there has the maximum concavity or the maximum positive curvature. So that means right here I've got the maximum erosion rate, and here I've got the maximum deposition rate. A lot of people got that one or the other of these at these upper points. I think in particular people got that the flux goes to 0 up here, but didn't also see that, well, since it's flat, the curvature also goes to 0 there. The erosion or deposition also goes to 0. In the keys that I've posted, I've put below here graphs of the topographic slope and of the topographic curvature, just to show that these, the bars that I put on there line up with places of extrema or zeros in those curves. Okay. Then the next one was, okay, I've got a LiDAR map, a hillshade map of the place in the Coast Range. And the question was, what's sort of the boundary, if you will, between fast erosion and slow erosion? I got a lot of right answers on that score, but then I said, explain your reasoning, and most people did not get that. Despite most people getting 1B correct, which says that the erosion/deposition rate is proportional to curvature. I then gave you a map and said, okay, where's the maximum erosion rate? And most people said the place where the slopes are steep. And I said, no. I mean, yes, but no. Place where the slopes are sharp. So actually, a few people just said, where the topography is rougher or smoother. And I gave you credit for that, because rough and smooth are what we perceive as we perceive curvature, high magnitude curvature as roughness, and low magnitude curvature as smoothness. So, yeah, that's the answer there. And I tried to tell you that several times. I know it, it's like, okay, here, do this, do that. Because again, I think I told you, you also knew that. Like, when you set up your sandbox experiments, you knew that those sharp ridges were going to erode the fastest, right? So when I'm looking at an entire landscape like this, such experimental conditions and some of the idealizations that we make are lost on parts of the landscape, but at those ridge tops, that's where we can really say something about, that right, there the erosion rate is probably going to be proportional to that ridge top curvature, and so we can infer what's going on in the entire landscape pretty well, at least in this case, from what those ridge tops look like, and essentially how broad they are. Oh, right, last one, Frost Creek. I tried to make this very simple in class, but the book made it more complicated, and so I had to actually go back on some of my grading and say, yeah, actually, once I read the book over what it said, some of you mentioned the solifluction that occur when you get the melting phase. Did you have a question?
Yeah, it was about the last question though.
Yeah.
So the erosion rate, or that's defined by the curvature of the ridges.
Mm-hmm.
But the curvature of the ridges is a property of that basalt intrusion that's stopping the creek?
No, the basalt intrusion is off the map, and that slowed down the southern part of that landscape.
So that is what is determining the slopes in this area though, right? Like on the south side of the ridge, that's why it's...
I mean, if you want to come up with an ultimate cause, I suppose, but I said...
Because if you didn't have that there with both
based
sides of the
only on the topography, all right? If you're basing it only on the topography, then you simply look at that and you go, oh, one place is eroding quickly, the other is eroding slowly. So since I said based only on topography, that's implying, don't figure that anything else is changing. And actually nothing else is changing really, except that the two different basins have different base levels effectively. Any other questions on that one? So the first part is the mechanism for soil expansion via frost heave the same as in frost cracking? Yes, of course it is. It's due to that heave pressure that's generated by ice crystal growth in the case of frost cracking in the small pores in the rock, in the case of frost heave in the pores of the soil or mobile regolith. And essentially if you said something about ice crystal growth, yes, ice crystal growth in both cases, that was the right answer. Ultimately, I would have liked you to say, yeah, it's heave pressure in both cases. Heave pressure breaks rock, heave pressure pushes up the earth. Describe the series of motions that lead to downslope transport. This is where if you actually read the book, you might have gotten it a little more complicated than I was after. I was simply after, okay, if I've got a slope and I've got ice lenses forming in there, then it expands outward normal. And when the ice melts, it drops back vertically, and hence I get a net downslope movement. As some of you mentioned that, okay, if I've got, especially if the freezing is relatively deep and it takes a while for the melting front, the thawing front to reach down, then you'll have frozen stuff down here blocking the escape of the water that's melting out of stuff above, and you'll essentially end up with a liquefaction or slight partial liquefaction of the material at the top, and it oozes. And that's especially that's a thing that's especially important in paraglacial environments. I don't know. I mean, but the book did show, well, if you look sort of at the micro level and you kind of zero in on, okay, yes, there's some element of it that is of the post of the thaw phase motion that is essentially straight down due to gravity, and some component of it which is downslope due to just the oozing of the material. Yeah.
Yeah, the book was saying that the offset due to jelly fluxion was more than the initial heave.
Yeah, that could be. I think. Well, let's say let's say that's true in the case that they looked at. I don't know if that's generally true. It may be. But I'm personally, I was just trying, in class, I was just trying to make it simple. It's like, okay, expansion, fall, you get net downslope movement. The amount of heave, is dependent on the amount of ice below or inward of you, and so that amount of heave decreases as you get down towards the freezing depth. So then the last question was, well, describe the conditions that increase the diffusivity associated with frost creep. We actually derived that in class. And we came up with that diffusivity is something like the strain, the mean freezing depth. I think those were the big two. Can't remember. I don't think there were. Oh yeah. Okay. So that was the frequency of freeze-thaw events. That was the strain on freezing. And that was the mean frost depth, the mean freezing depth. And that was squared. So if you wanted to get all mathematical or just, precise about it, you could go back and say, well, the diffusivity increases the square of the mean freezing depth linearly with the strain on freezing and linearly with the frequency of freeze thaw. Diffusivity does not, essentially by definition, increase with slope. I mean, you could argue against that. You could say, well, actually there is a slope dependence. Yeah, well, maybe I'll grant you that, but that's not what we talked about. Okay, okay, in certain ridiculously steep terrains that are still soil mantled, like the Oregon Coast Range, part of the reason you get planar slopes is that the diffusion law goes nonlinear. But, while I've acknowledged that, I said, well, but let's concentrate on where it's linear, because that's, that lets us say something about what's going on with ridge curvature and so on. So we defined a diffusivity that was, defined this way, where we say that diffusivity, or that the erosion/deposition rate is proportional to the topographic curvature. This comes out of the fact that the flux is proportional to the topographic slope, and that constant of proportionality is kappa times the bulk density. We have another bulk density that gets canceled out up here when we plug it in. Long story short, slope, yes. Transport rate, flux rate, yes, increases with slope. It's proportional to slope. The constant of proportionality is the diffusivity. By definition, does not change with slope. So, okay. Is that enough? Any questions on that quiz? Do you have a question? You just okay. Any questions on any of the other quizzes? Because we do have a test on Friday. Okay. I will just say a couple more words, just because you're going to ask. The midterm questions, let me put this succinctly. The set of quiz questions is the superset from which the subset of midterm questions will be drawn. Maybe not exactly. I do retain the right to edit the questions a bit, make them what I feel is more appropriate for a midterm rather than a take-home kind of situation. Yes?
Are we going to need to do any calculations?
Are you going to need to do any calculations? I don't think so. That's not to say that you won't be asked to talk about the equations for flux and for erosion/deposition, but no, I don't expect you to. You should not expect to have to do any actual number crunching. Yes.
Should we memorize some of these equations?
If you need to memorize it, if I ask you for the equation, the flux, diffusive hill slope flux equation, yeah. So again, anything that's on the quizzes is fair game. Again, I do try to keep in mind that the quizzes are take home, the midterm is not. On the other hand, I'm also trying to keep in mind that you know all the possible questions. So, there we go. All right. Last time we ended up with the factor of safety for stability of an infinite slope. So factor of safety is defined as the ratio of the opposite of the frictional strength or the shear strength to the shear stress. That is, we're looking at the ratio of things that are keeping it from falling and the things that are trying to make it fall. And this is the simplified form of that. It is on the top we have, transmogrified a bit by my algebraic simplification, on the top we have the friction and the cohesion. On the bottom we have the shear stress. And you can see it because the shear stress in particular right here, because in order to make this particular simplified form, I have to pull out the cohesion as a separate piece over here. This is a convenient form, if not immediately intuitive, because it lets us, it's easy to do some rough numbers with this one. So let me sketch up the slope again. There's our x direction parallel to the slope, our z direction normal. We've got some soil there, and a water table within it. Our soil thickness is capital H. Our water table thickness, H sub W. The slope is at an angle theta. And we've got material properties which are the bulk wet density, the angle of repose, and the cohesion. So I'm considering the cohesion due to roots as part of the material property of this earth material on the slope. So density, angle of repose, cohesion, soil thickness, water table thickness, slope angle. And we said that if the factor of safety is less than, let's say less than or equal to 1, then that implies a go or unsafe situation. That says that if this ratio is less than 1, the strength is less than the stress, and it moves. If the factor of safety is greater than 1, then that's a no-go, safe. But I'm going to put sort of a question mark in parentheses on that, because if our factor of safety isn't a lot greater than 1, we might start to want to look into, okay, exactly what is my uncertainty on some of these parameters. So that said, we can talk about 3 or 4 classes of slopes according to their cohesion, their water content, their angle, and whether they're safe, stable, no-go, or whether they're likely to be unstable. So first we'll talk about the always no-go case. Sometimes known as unconditionally stable. Even if I've got zero cohesion, even if my soil is saturated up to the ground surface, the slope angle is small enough for stability. So I look over here and I go, okay, what was that again? Okay, even with C equals 0 and HW equal to H, it's stable. So I look here and I go, okay, HW equal to H, that means that ratio is 1. Cohesion equals 0, this term goes away. And so what I'm saying then is that 1 minus the density of water divided by the wet bulk density of the material times the ratio of the friction slope to the ground surface slope, that is still always greater than or equal greater than 1. And what that then implies is simply that if I just multiply both sides by tan theta, I can solve for the slope at which this is true. Okay. Some rough numbers then. Rho sub W, 1,000 kilograms per cubic meter. Rho sub B, wet bulk density, say 2,000 cubic meters, 2,000 kilograms per cubic meter. So the ratio of the density is about a half, and so 1 minus a half, the quantity in parentheses here, about a half. So that means that as long as my slope is less than half of the friction slope, then I'm safe. Again, more specifically numbers, let's say that phi is 37 degrees, and so tan phi is 0.75. That means if I just plug through the numbers, which I won't do, full on, that my tan theta needs to be less than half of that 0.75 or 0.38. So that's pretty steep still, 38% slope, way steeper than they'd ever make a road for sure. And that corresponds to theta less than 21 degrees. So still feel pretty steep if you were on it, just not so steep that you'd feel like you were going to fall off. So that's our always safe slope. Even if we cut out the cohesion entirely, even if we saturate it entirely.
But only up to that angle.
Yeah, I mean, that's what I said. The slope angle has to be less than 21 degrees for it to always be safe. Our second class of slope would be the dry no-go and the wet maybe. Or low cohesion, maybe. In other words, if it's perfectly dry, if it's perfectly dry, then it's going to be safe. But if it's wet, especially if there's not so much cohesion, then maybe not safe. And we don't need to solve anything here to get this part. because we know that the dry material is going to be stable if the slope is lower than the angle of repose. And we know that it could become unstable if the slope is greater than 21 degrees when wet, if it's wet. So this is for slopes between 21 degrees and, in this case, 37 degrees, but that's equal to phi. So, in other words, our slope angle can be greater than the sort of always safe slope angle that we came up with here, or that we would come up with for a given material. But it's less than the angle of repose, and so essentially, yeah, you gotta do the calculations. So in this case, if we have no water table, then it's a no-go. And if we have a water table and low cohesion, it's a possible go. We have a third class of slopes that somehow manages to be soil mental despite the fact that the slope is actually greater than the angle of repose. This is what you might call the really? That is, if there's no cohesion, then it's a go. And that means that the slope angle is greater than the angle of repose. So if cohesion ever goes to 0, it's going to go. And if we've got a water table, low cohesion, it's a possible go. So especially if you were in my van coming back on the field trip, and I kept sort of stopping and looking for boulders to shove off the hill, off the road. A, that's fun to do, mostly. But B, it's instructive because what it tells you is, if I want to know about something about landsliding in the Oregon Coast Range, the question is not so much what made it fail, but what the heck keeps it from falling apart. If I roll a boulder down that slope, it doesn't stop until it either reaches the bottom or it hits a big enough tree to stop it, or it breaks upon hitting a tree, you know. And that's because most of the Oregon coast, a lot of those Oregon Coast Range slopes are at like 40, 41 degrees, which is greater than the angle of repose of the unvegetated material. But because there are roots giving it lateral cohesion, because there is some surface roughness, ferns and all the other stuff in the understory that keeps little rocks from rolling over the surface. or even larger rocks from rolling over the surface, it doesn't completely unravel until you burn it off. And if you hit that stuff with a big fire, the material just ravels off in a matter of hours to months. Okay. We could consider potentially a fourth class. Stuff that's just so wicked steep it can't ever have soil on it. So bedrock slopes. Doesn't really fit into our math. Even bedrock slopes will become unstable depending on the strength of the material, but we're not going to go there. It's interesting. These are sketchy places to walk around on. Piles of rocks. I do want to go a bit farther though with this example, or take an example of this number 3 here. In part, I find it interesting because I've spent a lot of time in the Oregon Coast Range doing field work, looking at landslides, looking at debris flows. So in the Oregon Coast Range, the typical slopes of those hills are upwards of 40 degrees. So take the example, number 3, Oregon Coast Range. And specifically, I guess I'd say the Tyee Formation part, southern to central Coast Range, where we've generally got theta greater than or about equal to 40 degrees. Not everywhere, of course, but a lot of the slopes are sitting that steep. So one question is, how much cohesion is necessary to keep it stable if the water table rises to the ground surface? And of course, I erased my master equation, but I'll have to write it up again. So in that case, we're talking, so if our water table thickness equals our soil thickness, then the factor of safety is simplified somewhat. Because these cancel. And I'm just going to erase those men for the sake of giving myself the space. Then we've got our ratio of tan theta to tan phi, and our cohesion term and we want to know when is that going to be greater than 1? And what's the cohesion at that point? I think I should probably just spare you the algebra. I don't expect you to do it. But what you come up with is that I'm going to need cohesion greater than this little beast of a formula here. Yeah.
Why did the tangent relationship become
because I had to move it. Oh, no, you're right. That was a different one. Thank you.
I want to drop it,
Thank you. Right. Okay. If I go through the example, let's just say, okay, rho W over rho B is 1/2. Angle of repose, 37 degrees. Slope angle, 40 degrees. And my wet bulk density, 2,000 kilograms per cubic meter. And so let's just say soil depth equals 1 meter. Of course, gravity is 9.8 meters per second squared. One of the things we can notice from here is that my necessary cohesion, so this is the cohesion necessary for stability given full saturation, that is proportional to the soil depth or the soil thickness. So this 1 meter number here gives me that I need cohesion greater than about 7 kilopascals. But if I'm, say, in the range of 1/2 meter thick soil to 2 meter thick soil, then my cohesion needs to be in the range of between 4 kilopascals and 14 kilopascals. Let's look at some data. So remember what we're saying. We're saying, okay, wicked steep slope. Let's imagine the mother of all storms saturates the soil all the way to the surface, and yet it's possible that it could still be stable if we have enough, specifically if we have enough root cohesion. Because there's no soil that I know of that's going to give us that amount of cohesion on its own. Typical soil cohesions are about 500 pascals. Okay, so here's some data. This is Josh Roaring and Kevin Schmidt. Josh is at U of O, Kevin Schmidt's with the USGS now, but when they were grad students, they went and tugged on roots until they broke in soil pits that they dug themselves or in landslide scarps. And they did it for lots of different classes of forests or root types or what have you here. Natural forest pit, inferred natural forest landslide in Mapleton, natural forest blowdown, industrial, blah, blah, blah. Okay. ESF is Elliott State Forest. And roughly speaking here, we've got younger to older. I'll show you a different plot where I've actually tried to assign some ages to those. And we see lateral root cohesion on this axis in kilopascals. This is a log axis. This is a more or less linear axis. And you see that the root cohesion just keeps getting bigger. I wish they had gone ahead and made a graph like this one. Just gone ahead and put some numbers on those ages and put a fit to it to tell us how root cohesion increases with time. since I wanted them to do it and they didn't, I did it myself. So on this axis, we've got time since disturbance in years axis going from 0 to 350 years. Here we've got similarly lateral root cohesion in kilopascals, similarly a log scale. And their data, estimated ages put on there, and then an exponential fit to it. 57% R squared, not awesome, but not awful, given the fact that this literally comes from tugging on roots until they break. And what we see is that, yes, since we put a straight line on this semi-log plot, that means it's an exponential function. The little constant that I'm sure probably none of you can see is 0.01, or 1 times 10 to the minus 2. That means we get 1% increase in root cohesion per year. And according to their data, without bound. I mean, at least they did not find the end of that increase in their data. I've put up here the range of about 4 kilopascals to 14 kilopascals, and then projected that off of the trend through the data. And that essentially says that anything, forests in the range of, say, 15 years, and this is time since disturbance, so, forest fire, and then you start the clock, or something along those lines. 15 years to 160 years is our time period of heightened risk or potential instability. Less than 15 years is quite dangerous, I suppose. But this is essentially, okay. Again, this is if I fill it to the brim with water, and the ranges of that thickness are about 0.5 meter to 2 meters, then I get this range of necessary cohesion corresponding to this range of necessary age of forest in order to impart stability. So we can see, for a 0.5 meter thick soil, as long as our forest is older than 15 years, maybe we're out of the danger zone. But if we're in places where the soil is deeper, then we can still be in the danger zone up over 150 years. Which is a lot longer than we tend to think of the danger zone being. We tend to think of danger zone is, well, the maximum danger is about 4 or 5 years, and then we start getting out of the woods, so to speak, after that. And what this says is, yeah, once you get to 15 years, you'll be all right as long as your soils aren't very thick. And in a lot of the Coast Range, they aren't. 0.5 meter, is not a bad estimate for a lot of soil thicknesses in the Coast Range. However, not so great otherwise. And I think I will just stop there, since it is 11:50 according to this clock. Next time we will deal with such things as, well, how does the water get there? Or how do we think about or calculate or estimate how much water there might be at a given soil column? We'll talk about how fast, or what happens once it fails. Does it accelerate or decelerate? That's a good thing to know. Short answer is if it's compacted, it decelerates. If it's not, it accelerates. But we'll talk about that. Of course, next time is actually the exam. By next time, what we're going to talk about, that's Monday, but Friday is the midterm. Yes?
Do you have a quiz?
No quiz this weekend, so I'm going to have to pile on to you next